Hello everybody, and welcome to the top of page 132 in the workbook. And we're going to take a look at a definition that's going to kind of pave the way for what we want to do in the next section. All right, so let's read this together. There are two pieces to it. So we're starting with an inner product space V. And the first thing that we want to talk about is the idea of a subset of S being orthogonal. What does that mean? Well, a set is orthogonal if any two distinct vectors in the set are orthogonal to each other. Okay, let's just give a quick example of that. Just maybe in R3, since that's a nice familiar vector space. So if we took S1 to have the three vectors 1, 0, 0, 0, 2, 0, 0, 0, 3, notice that every vector in that set is orthogonal to the other two in the set. Okay, so you could say that all three of those vectors are mutually orthogonal, and therefore that this is an orthogonal set according to this definition. Okay, and then the second piece of this definition has to do with something called a unit vector. Okay, a unit vector is just a vector whose norm is equal to 1. That's the same definition that you might remember from multivariable calculus, same idea. And now that we have a definition of a unit vector, we can talk about something called an orthonormal set. Okay, an orthonormal set of a vector space is just a set of vectors that are not only orthogonal, but also consist of unit vectors. Let's give an example of an orthonormal subset of R3. You will probably recognize this as being a very important subset. Notice that all three of those vectors are mutually orthogonal and they're unit vectors. They have a length of 1. You might recognize those as the standard basis vectors, I, j, and k from multivariable calculus. So that is an orthonormal set in R3. And we will see that sets like this are very nice. We can do some really great things with these, and we will explore that in more detail in the next section.